Alright, so this is our introduction to Chapter 5, and Chapter 5 is all about something called a normal distribution. Okay, and a better name for a normal distribution that you might be familiar with is the bell curve. Okay, we say something that is normally distributed, meaning that it looks like a bell curve when you graph it. So I'm going to show you in this section how to interpret those graphs and then how to find areas under the curve. And by the way, this is the biggest concept that I want to mention to you. Area under the curve is synonymous with probability. So if you can understand that, you are a good way towards understanding things of this chapter. For example, all of this area under the curve, that's 100% of the area. Okay, so if I asked you, what's the chance that you'd be below the red line, that's half the curve, so there's a 50% chance. So that's what we mean by area under the curve. Okay, a couple concepts of the terms that you will see. In Chapter 4, we talked about discrete probability, meaning the number of successful free throw shots. You could make 4 or 5 or 6. You couldn't make 4.5 and stuff like that. In this chapter and in future chapters, we'll be talking mostly about continuous probability. So things where you could go, for example, between 4 and 5 or 5 and 6. And usually those are things that you can measure, like somebody's height. They could be 6 feet or 6 feet 1 inch or 6 feet 1.347 inches or whatever. Okay, the normal distributions bell curves show up all over the place. They're giving some examples here. The blood pressures of people. Most people have a blood pressure that's somewhere around average, and then some people have very low blood pressure, and then over here some people have very high. Okay, and they talk about it. Housing costs, TV lifetimes, etc. It shows up all over the place. Best example would be grades. The average grade is supposed to be a C, and then there's supposed to be fewer people who have B's and very few who have A's, and vice versa on the other side. Okay, that's not how it works today because of grade inflation, but that's what it's supposed to be. Average grade theoretically is supposed to be a C. All right, here are the conditions for a bell curve or a normal. Really, the technical name is normal curve. These three things are equal on a bell curve. The average is right in the middle, so is the median, so is the mode. Okay, it is symmetrical, and you'll see a picture. Total area under the curve. Remember, I told you area under the curve means probability. The probabilities add up to 100%. Okay, the area adds up to 1. Okay, the probability never touches the x-axis. You'll never have a 0% chance. Okay, so obviously, let's say we're doing average height, right? The average height, let's say, is 5 feet 10 inches, hypothetically. Okay, this person, like way out here, that's like a 11-foot tall person. And even though we've never seen such a person, there is a incredibly, incredibly small chance that somebody will have some sort of pituitary gland problem and they'll grow to be incredibly tall. And vice versa, there is an incredibly small chance over here that somebody will be, the size of an amoeba or something like that. Okay, so the probability is never completely 0. Okay, and then this stuff right here just talks about kind of the direction that the curve is happening, and these are called inflection points. That curve or that break occurs right at 1 standard deviation away from the mean. Okay, and the technical name for that is inflection points. You study those in calculus, but you don't need to know calculus to understand this. Here's the picture. They're showing you the inflection points. This inflection point occurs right there, and you can see the mean is there. That's 1 standard deviation, and there's 1 standard deviation the way. The inflection point just means where does the graph start to kind of curve almost. You can picture it like this is like an upside down glass, and right at this point the glass would start to face right side up. So the water would go in this direction versus up here it would go upside down. Okay, if that confuses you, just think of inflection point as either 1 standard deviation more or 1 less than the average. All right. This is the actual way that you can produce the curve. If you're wondering what's the function that produces that curve, it looks like that, and I graphed this on Desmos. You can see that's not a great bell curve because I didn't zoom in enough, but this is the sort of thing that you would study in a calculus-based statistics class, I should say, which this is not, so you don't have to worry about it. Here are a couple pictures of 3 different curves that all have the same average, but you can see that the deviations change. Okay. So the deviation on this one and this one, 0.7. Okay, the deviation on this one, 1.5. So you can see this has a larger deviation that causes the bell curve to get spread out more. Okay, so that is kind of what that would look like right there. This one right here, the mean is at 1.5, and they just kind of distorted the graph by putting more of a tail over there than they needed to. The mean is not kind of right nicely in the middle. All right, let's take a look at this example so we can answer some questions. Which curve, so they're talking about curve B or curve A, which has the greater mean? See if you can answer these yourself before I tell you. And then which has the greater deviation? So the greater mean, well, the mean on curve B looks like it's at 12. That's right in the middle. and the mean on curve A looks like it's 15. So 15, A has a mean of 15, that's greater than 12. Which has a greater deviation? Which is more spread out? Well, you can probably tell from looking that this one right here goes from 12 and the inflection point is at 9 and at 13. So this one has a deviation of 3 because you're going 3 above or you're going 3 below. What about A? A goes from 15 to, and the inflection is a little bit harder to see here, but it looks like right about there. So what is that? Maybe 16 and a half or 17. And this one is about maybe 13 and a half or so. So that deviation looks like it's only about 1.5 possibly. So the deviation is not as large on A as it is on B.